Okay, so I guess I should begin. You might be curious why this is part 5 when the first 2 talks were parts 1, 2, and 3. And that was because I had actually put together parts 3 and 4 for yesterday's talk. And because the material covered was twice as long as in a normal talk, the talk actually took half the time. So we'll see what happens today. Also, given the unpredictability of the length of my talks, someone had asked if I have time at the end, if I would make some remarks about Erdos, who had been a frequent visitor to India. So we'll see what happens. Okay, so let's go back to the beginning, the additive Erdos-Turan conjecture. So you have a set of non-negative integers, and what I'll call the additive representation function, R of n, counts the number of ways to write n as a sum of h elements from the set A. And we say that A is an additive asymptotic basis if every number from some point on, for all n greater than or equal to n naught, every number has at least one representation. And in 1941, Erdos and Turan asked if the representation function of every additive asymptotic basis of order h must be unbounded. That is, to be an additive asymptotic basis, the lim inf is at least 1. And the question is, does that imply that the lim sup is infinity? And that's unsolved even in the first case, h equal 2, which is in fact the only case that Erdos and Turan stated. I just want to make one quick remark, because I didn't mention this previously. A set of non-negative integers is an additive basis. I dropped the word asymptotic. If not every sufficiently large, but every non-negative integer can be represented as the sum of h elements in the set. If you have an additive asymptotic basis of order h, again, that means that for all integers n greater than or equal to n naught, every number has a representation. So if you take the set A and you adjoin these n naught integers, 0, 1, 2, up to n naught minus 1, call that set A prime, we now have an additive basis of order h. Every number is represented. And because we added some numbers, the representation function for the set A prime is at least as large as the representation function for the set A. So if you want to prove the Erdos-Turan conjecture, it's enough to prove it for additive bases, not additive. You don't need to restrict, which is a smaller class than additive asymptotic bases. But I want to look today at the multiplicative analog of the Erdos-Turan conjecture. So now we take a set B of positive integers, and for every positive integer h, we write down a multiplicative representation function, g of n. So this counts the number of ways you can write n as an ordered product of h elements from the set B. And we say that B is a multiplicative asymptotic basis, multiplicative, of order h if every number with a finite number of exceptions can be written as a product of h elements from the set A with repetitions allowed. Now, there's no reason to imagine why the additive or the multiplicative version of the Erdos-Turan conjecture should be more difficult than the other. And I don't know which is more difficult. We just know that we have a proof of the multiplicative version. And in 1964, Erdos, in fact, proved this multiplicative analog of the Erdos-Turan conjecture. So what he proved is that for every h at least 2, the multiplicative representation function of a multiplicative asymptotic basis of order h is unbounded. That is, if the lim inf of the multiplicative representation function is at least 1, then the lim sup is infinity. And his proof was sort of combinatorial and graph theoretic, and there was a later proof by Nathanson and Erdos using Ramsey theory. So the conjecture is true. But we can look at something slightly more general. And now let's take a system, or an H tuple of different, or not necessarily the same sets of sets of positive integers. So B1, B2, B3 up to B sub h, this is an ordered h tuple of sets of positive integers. And we can consider representations of an integer n as a product B1, B2, B3 up to B sub h, where Bi comes from the set capital Bi, B2 comes from the set capital B2. There should be some dots there in the middle. So we have this sort of slightly more general representation function for an h tuple of sets. If all the sets were the same, this would just be the multiplicative bases or multiplicative problem we looked at a moment ago. So we take here an h tuple of sets of positive integers, and we want to count the number of ways to write a number n as a product. And we say that this h tuple is a multiplicative asymptotic system of order h. So I don't want to use the word basis. That's just when all the numbers come from the same set. A multiplicative asymptotic system of order h if every number from some point on has at least one representation, and a multiplicative system of order h if every positive integer has at least one representation. So what's an example of a multiplicative system? So take the set P of prime numbers and partition it into h pairwise disjoint sets. And for I going from 1 up to h, let Bi be the set of the set of integers, all of whose prime factors belong to the set Pi. So the set B1 is all numbers which are products of primes in P1. B2 is all numbers which are products of primes, powers of primes in P2, and so forth. So we look at this system of H sets. And the fundamental theorem of arithmetic simply says that every positive integer has a unique representation. In other words, the lim_inf and the lim_sup are 1. So the analog of the Erdos conjecture for multiplicative systems is false, right? However, it's very dramatic. We have a theorem. See, the Erdos conjecture would say if the lim_inf were 1, the lim_sup would be infinity. But we know that's false. But what is true is if the lim_inf is at least 2, then the lim_sup is infinity. All right? So if you have a system of sets of positive integers where every number from some point on has at least two multiplicative representations, then the representation function has to be unbounded. So that's the theorem I'm going to prove today. Right? I mean, I proved it a long time ago, but it is the theorem du jour. Actually, we generalize this slightly, or we make it a little bit more precise. So for every h greater than or equal to 2, I want m of h to consist of all pairs of integers s and t, such that for some asymptotic multiplicative system, the lim_inf is s and the lim_sup is t. Right? So for example, we know that the pair 1, 1 is in m of h, because we had that example with the primes. But I want to know all pairs st, such that for some multiplicative system, the lim_inf is s and the lim_sup is t. And the answer, it's sort of stuck here at the bottom of the slide, but it'll come up, I'll repeat on the next slide. This is what m of h is. You can have lim_inf equal to 1 and t every number from 1 up to and including infinity. Yes. Well, actually, let me just read the way it's written. 1 comma t, so the lim_inf 1 and t any positive integer, or you can have s equal 1 to h, s equal to 1 infinity, but the only possibilities for s are 1 up to h, and for 2 up to h, the only possibility for t is infinity. So this is just a more precise statement of the theorem. Sorry? I'm sorry, I can't hear. Yes. So m of h, it's a set of pairs of integers. So M of H is pairs ST, where for some multiplicative system, S is the lim inf, and T is the lim sup. So you can have S equal to 1, and T any number from 1 to infinity. Each of those occurs. What? Yeah, they're ordered pairs. Yeah. Pairs, ordered pairs of positive integers. So first we'll show that, so the theorem says this set on the left equals this. So first I'll show that this is contained in this, that every one of these pairs can occur. And this is done just by simple construction of examples. So suppose we take any number t, either a positive integer or infinity, and I write down a system of h sets as follows, b1 up to bh. So b1 is the positive integers. That's what capital N is. b2 is the first t powers of 2, if t is finite, or all powers of 2 if t is infinite, and all the other sets in the system just consist of the number 1. So what can we say? First of all, when you write down a number as a product, of course, the factors 3 up to h, they're all going to be 1s. Here, you have at most t choices. And once you pick a power of 2, that determines the complementary factor from b1. So an upper bound for the representation function is t. And for any number n, you can just choose n and b1 and all the other numbers to be 1. So every number has at least one representation. So this multiplicative representation function is bounded between 1 and t. But of course, if you start with an odd number, you can't pick a positive power of 2. You only can pick a 1 here. So for an odd number, the only representation of n is n times 1 times 1 times 1, and so forth. So because g of n is 1 for all odd n, the lim inf is 1. This is that same set. So we write this notation, 2 to the u and 2 lines n means 2 to the u is the exact power of 2 that divides n. So 2 to the u divides n, but 2 to the u plus 1 does not divide n. So if you take u between 0 and strictly less than t, and a number n, which is exactly divisible by 2 to the u, then we have these u different representations of n. Right? So for k going from 0, 1 up to u, 2 over n over 2 to the k, that's an integer. Choose that from the set b1, 2 to the k from the set b2, and the rest 1s. So if t is a finite number, an integer, choose u to be t minus 1, choose an n divisible exactly by 2 to the t minus 1. There are infinitely many of them. And you'll have infinitely many numbers where integers n, where the representation function, the g of n, is exactly t. And if t is infinity, that is, if you have every power of 2 here, you can choose u arbitrarily large, but in all cases, or in both cases, the lim sup is t, whether t is finite or infinity. So let me just go back to, all right. So that says that 1 comma t, for every t, every integer t together with infinity, they're elements of this set M of H. That P be the set of prime numbers. So I want to write down another multiplicative system. For every S between 2 and H, look at the multiplicative system, which is the following. Oops. Oops, where are we going? I keep pressing the wrong buttons. I'll try it again. So So this is a multiplicative system. B1 up to BH. The set B1 is all the positive integers. For B2 up to B sub S, you take the primes together with 1, and for the remaining H minus S sets, let them all be equal to 1. So if you choose a number n with k distinct prime factors, then the number of representations will be at least k, because you have, for example, if p is a prime factor of n, you can take n over p from the set B1 and p from the set B2 and everything else equal to 1. So if k has n distinct prime factors, then the number of representations is at least k, and so the lim sup is infinity. Okay, so this proves the easy part, that every one of these pairs, 1 comma t and s comma infinity, 1 up to h, are all elements of the set M of h. And I want to show there are no others. Okay. Suppose we have an asymptotic multiplicative system of order h. So if you take a prime p, the only way you can write p as a product of h numbers is if one of the numbers is the prime and the rest are all 1. So for a prime, the number of representations is at most h. So the lim inf is always no greater than h. So in these pairs st, s is at most h. S is going from 1 to h, but it can't be any bigger than h. So the only thing left to prove is that if we have a multiplicative system where every number from some point on has at least 2 representations, then the lim sup of the representation functions has to be infinite. And for this, we use Ramsey's theorem. Now, so I know Ramsey's theorem has been discussed in previous talks, so I'm certainly not going to, I'm going to state it at some point. But I'm going to go through the proof of the theorem. And there's a one point at which I need a lemma, which uses Ramsey theory. So as not to interrupt the proof, I will say, by the lemma, this is true, and then we've done with the proof, and then I will show you the lemma. Okay. So let B1 up to B sub h be an asymptotic multiplicative system of order h. So every integer, with maybe finitely many exceptions, can be written as a product of an element from B1, an element from B2, an element up from B sub h. So this is sort of standard notation in Ramsey theory. If you take the set P of primes, the square brackets P and the superscript less than omega is the set of all finite sets of prime numbers. That Q be the quadrafri, the positive square-free integers. And if you take a square-free integer, you can let S of Q be the set of all the primes that divide Q. And this is a finite set of integers. And conversely, if you take any finite set of integers, if you take any finite set of primes and you multiply them together, you get a square-free number. So there's a one-to-one correspondence between the positive square-free integers and finite sets of primes. So I'm going to construct a new sort of a system of sets. So A sub I is going to be what? So we have these h sets of positive integers, B1 up to B sub h. So look at B1 and take all of the square-free numbers in B1. That's Q intersect B1. Q is the set of square-free numbers. For every Q square-free number in B1, take the set of its prime divisors. So AI, for every I, is a set of finite sets of primes. So this is a subset of the finite sets of primes. And look at this system of H sets. So each set, again, each of these sets, A1, A2, up to A sub H, is a set of finite sets of prime numbers. The square brackets P to the D be all sets of prime numbers that have cardinality D, all sets of exactly D prime numbers. So for an asymptotic multiplicative system B, we're only considering systems where the lim inf is, actually this should be the lim inf is S greater than or equal to 2. So where the lim inf is at least 2, that means that every integer has at least 2 representations with finitely many exceptions. So for every D, and for all but the most finitely many sets of D, so S is a set of D primes, this equation has at least 2 solutions. So S is a set, a finite set of primes. If you take a square-free number and you let S be the set of primes that divide that square-free number, that's what we look at that as, that's what the set S is. Now, this square-free number has at least 2 representations as a product of elements from the set number, the sets B1 up to B sub H. If you write a square-free number as a product of numbers, each factor is square-free. So if you're happy or able to go back and forth between products of prime numbers and unions of sets of primes, we have that in the set theoretical context. Every set S, with finitely many exceptions, has at least 2 representations as in this form. The lemma, so this mysterious lemma implies that for every n, there is a square-free number q where g of q has at least n representations, and that means the lim sup of this multiplicative basis is infinity. So applying some mysterious lemma, we're done, right? So this mysterious lemma says something like the following. A1, so I had a collection of sets, of finite sets of primes. A1 is a finite set of primes. A2 is a finite set of primes. AH is a finite set of primes. And each of these finite sets of primes belong respectively to those sets, script A1, script A2, and so forth. And S, this set of finite set of primes, is a union of these sets. And there are at least 2 solutions of this sort of set theoretic equation. And there's going to be a lemma that uses Ramsey's theorem that says, whenever that's the case, there's some set S that has at least n representations as a union. And when you translate from that back to square-free numbers, that says there is a square-free number that has at least n representations. So g of q for some square-free number is at least n, and so the lim sup is infinity. Okay. So that proves the theorem, but I have to say something about what this lemma is. Okay. Oh, sorry, but let me also show right away. This implies Erdős' theorem. So if you take an asymptotic multiplicative basis of order h, Erdős proved the lim sup is infinite. So, of course, there are 2 cases. If for your basis b, the representation function has a lim inf at least 2, then you take the multiplicative system where every set is equal to b, and the result follows immediately from the theorem. So suppose the lim inf is 1. So you have a multiplicative system where infinitely many numbers have exactly 1 representation. Now, that means that every number, if the representation is 1, it means your number has a unique representation. But we're looking at ordered representations. If we permute these factors, we would get a different representation unless the factors are all the same. So in fact, this number n with a unique representation has to be just a pure power, a pure hth power. In particular, if n is square free, it's not an hth power, its representation function has to be at least 2, and just as in the theorem, we can prove that implies that the lim sub is infinity. So, okay. Ramsey. So for any set x, we denote by x to the k all subsets of x of cardinality k. So we have the pigeonhole principle, the finite form, and the infinite form. The infinite form says if you have an infinite set and you divide it up into a finite number of pieces, one piece has to be infinite. And Ramsey's theorem just generalizes this a little bit. So what Ramsey's theorem, so the infinite pigeonhole principle is just the case k equal 1 of Ramsey's theorem. So if x is a countably infinite set and k and r are positive integers, take all the k element subsets of x and write it as a union of r subsets. And Ramsey's theorem says there is an infinite subset y of x such that all of the k element subsets of y belong to exactly one set in this partition. All right? That's Ramsey's theorem. And there is a sort of an iterated version which says the following. If you have a countably infinite set, and suppose that for every positive integer k, you can partition the k element subsets of x into r sub k subsets, right? So for every k, the k element sets are partitioned into a finite number of pieces. The number of pieces depends on k. Then there exists an infinite decreasing sequence of sets. X contains x1, x2, and so forth. Infinite. This is an infinite decreasing sequence of infinite subsets of x and a sequence of integers s sub k, such that if you look at the kth set in this system, all of its j elements all of its j element subsets belong to one piece in this partition of the j element sets simultaneously for all j from 1 up to k. That is, you start with x, x1's an infinite set, you have a partition of the one element subsets, that just means a partition of x. Infinitely many sets are in one set in the partition, so x1 is just that infinite subset of x. Take x1, the two element subsets of x are partitioned. That means the two element subsets of x1 are partitioned. So x1 contains an infinite set, all of whose two element sets lie in the same cell in the partition, and so forth. So this is the iterated form of Ramsey's theorem. And this is the lemma that is sort of the sledgehammer that kills the proof of, that proves the theorem. So h is at least 2, x is a countably infinite set, and we have some system of finite subsets of x. So script A1 is a set of finite subsets of x, similarly for A2, A3, and so forth up to A sub h. Let D be an infinite set of positive integers, such that, and really all that means is D contains arbitrarily large integers. So that if D is an element in the set capital D, if you look at the D element subsets of x, this set theoretical equation, exactly what we were looking at in the proof of the multiplicative basis theorem, has at least two solutions where the set AI is in script AI for I equal 1 up to h. Conclusion, right, that's what we prove. What's proved is that for every n, there's some finite set T of a subset of X, so that you can write T as a union of H sets, each from one of the appropriate one of these partitions. But we have n different such representations, and moreover, in these representations, these sets are pairwise disjoint. So if you use the correspondence between square-free integers and finite sets of primes and move back and forth, this was the key step that proves that in a multiplicative system, if the lim_inf is at least 2, that means this type of equation has at least 2 solutions, then there are numbers which have at least n solutions. So I'm not going to go through the proof. I mean, the slides, I guess, will be available, and I actually put the proof in the slides. Well, I guess you've seen a proof, but I mean, it's hard. I mean, it's hard to work through. So the original paper of Erdos was this paper in the Israel Journal. About 20 years later, Nathanson and Redel gave a very beautiful proof using Ramsey's theorem, and I liked their proof, so I stole it to prove a somewhat more general theorem. I will say that Erdos was surprised at the theorem about multiplicative systems. I mean, Erdos thought about this for a little bit, a microsecond perhaps, and he saw the example that if you take the primes and write them as a union of a finite number of pairwise disjoint subsets, you get a multiplicative system where every number has a unique representation. So the Erdos-Turan multiplicative analog isn't true. And he stopped. And it just turned out that if you have a multiplicative system where there are these 2 representations, then there have to be arbitrarily large representations. Okay. All right, well, so that's my talk. That's my mathematics talk. So I'll say a few words about Erdos. I actually have something here, but it is probably above my skill level to find it. So, what? Yes. So when this was put on the computer, and just before my talk, there was a second file about Erdos that was put on. So you have to get to the directory. So wherever this file is, in that same subdirectory, or whatever they call it in PC language. Oh, that's it, Erdos Paradox. Okay, and if it's possible to blow it up. So it's, okay. Oh, fantastic, I think. Okay, so Erdos died in 1996. When I realized that this morning, I was thinking, it only seemed like a couple of years ago, but that's like 24 years ago. And so, of course, he was going to have a funeral in Budapest, and a number of people went to the funeral, mathematicians from Hungary, of course, Eastern Europe, Western Europe, and 2 Americans, Ron Graham and I. And because the people at the Math Institute knew that there were going to be a number of foreign visitors, they decided they would have a little conference in memory of Erdos for a day or two after the funeral where people would talk about Erdős's work. And I was asked to chair one of the sessions and to say a few words about him as opposed to about his mathematics. So I actually wrote out something on my computer and said this stuff. And then when I got back to the States, someone asked me for a copy, so I emailed it to them. And evidently, it was somewhat controversial what I said. I'm not exactly sure why. So I wrote up this little article about the event, and it sat on my computer for a very long time, and partly because no one would publish it, because it really was sort of evidently controversial. Though at the time, now no one can remember why. And at some point I said, I just put it up on archive, and some people read it. And there's a volume that comes out every year. It's published by Princeton University Press. It's called Best Writing in Mathematics, 2017, 2018, every year. And it's a collection of expository articles about mathematics. And the editor asked me if he could include this little essay. It's only 2 or 3 pages. Include the essay in the volume. And I said, sure. So I'm going to just basically read this, and then if there are any questions at the end, I'm happy to talk about it. The Erdos Paradox. So the great Hungarian mathematician Paul Erdos was born in Budapest on March 26, 1913. He died alone in a hospital room in Warsaw, Poland, on Friday afternoon, September 20, 1996. It was sad and ironic that he was alone because he probably had more friends in more places than any mathematician in the world. He was in Warsaw for a conference. Vera Soch had also been there, but had gone to Budapest on Thursday and intended to return on Saturday with András Sarkozy to travel with Paul to a number theory meeting in Vilnius. On Thursday night, Erdos felt ill and called the desk in his hotel. He was having a heart attack and was taken to a hospital where he died about 12 hours later. No one knew he was in the hospital. When Paul did not appear at the meeting on Friday morning, one of the Polish mathematicians called the hotel. He did not get through, and no one tried to telephone the hotel again for several hours. By the time it was learned that Paul was in the hospital, he was dead. Vera was informed by telephone on Friday afternoon that Paul had died. She returned to Warsaw on Saturday. It was decided that Paul should be cremated. This was contrary to Jewish law, but Paul was not an observant Jew, and it is not known what he would have wanted. Nor was he buried promptly in accordance with Jewish tradition. Instead, 4 weeks later, on October 18, there was a secular funeral service in Budapest, and his ashes were buried in the Jewish cemetery in Budapest. Erdos strongly identified with Hungary and with Judaism. He was not religious, but he visited Israel often and established a mathematics prize and a postdoctoral fellowship there. He also established a prize and a fellowship in Hungary. He told me that he was happy whenever someone proved a beautiful theorem, but that he was especially happy if the person who proved the theorem was Hungarian or Jewish. Now there has to be a way to go to the next page.
On the right side.
On the right side. Okay. So mathematicians from the US, Israel, and many European countries traveled to Hungary to attend Erdős's funeral. The following day, a conference entitled Paul Erdos and His Mathematics took place at the Hungarian Academy of Sciences in Budapest. And mathematicians who were present for the funeral were asked to lecture on different parts of Erdős's work. I was asked to chair one of the sessions and to begin with some personal remarks about my relationship with Erdos and his life and style. This paper is in 2 parts. The first is the verbatim text of my remarks at the Erdos Memorial Conference in Budapest on October 19, 1996. 1996. A few months after the funeral and conference, I returned to Europe to lecture in Germany. At Bielefeld, someone told me that my eulogy had generated controversy. And indeed, I heard the same report a few weeks later when I was back in the US. 18 years later, on the 100th anniversary of his birth, it is fitting to reconsider Erdős's life and work. So this is the eulogy at the Budapest meeting. I knew Erdos for 25 years, half my life, but still not very long compared to many people in this room. His memory was much better than mine. He often reminded me that we proved the theorems in our first paper in 1972 in a car as we drove back to Southern Illinois University in Carbondale after a meeting of the Illinois Number Theory Conference in Normal, Illinois. He visited me often in Carbondale, and even more often after I moved to New Jersey. He would frequently leave his winter coat in my house when he left for Europe in the spring and retrieve it when he returned in the fall. I still have a carton of his belongings in my attic. My children, Becky and Alex, who are 5 and 7 years old, would ask, when is Paul coming to visit again? They liked his silly tricks for kids, like dropping a coin and catching it before it hit the floor. He was tolerant of the dietary rules in my house, which meant, for example, no milk in his espresso if we had just eaten meat. He was tough. No illegal thinking, he would say when we were working together. This meant no thinking about mathematical problems other than the ones we were working on at that time. In other words, he knew how to enforce party discipline. If you know Communist Party rhetoric, this is all, technical language. Erdos loved to discuss politics, especially Sam and Joe, which in his idiosyncratic language meant the USA, Uncle Sam, and the Soviet Union, Joseph Stalin. His politics seemed to me to be the politics of the 30s, much to the left of my own. He embraced a kind of naive and altruistic socialism that I associate with idealistic intellectuals of his generation. He never wanted to believe what I told him about the Soviet Union as an evil empire. I think he was genuinely saddened by the fact that the demise of communism in the Soviet Union meant the failure of certain dreams and principles that were important to him. Erdős's cultural interests were narrowly focused. When he was in my house, he always wanted to hear noise, that is music, especially Bach. He loved to quote Hungarian poetry in translation. I assume that when he was young, he read literature. How do we turn this page? Oh, I did. He was amazed that Anatole France is a forgotten literary figure today, but I don't think he read much anymore. I subscribed to many political journals. When he came to my house, he would look for the latest issue of Foreign Affairs, but usually disagreed with the contents. Not long ago, an American historian at Pacific Lutheran University published a book entitled Ordinary Men, a study of how large numbers of ordinary Germans, not just a few SS, actively and willingly participated in the murder of Jews. He found the book on my desk and read it, but did not believe or did not want to believe it could be true because it conflicted with his belief in the natural goodness of ordinary men. He had absolutely no interest in the visual arts. My wife was a curator at the Museum of Modern Art in New York, and we went with her one day to the museum. It has the finest collection of modern art in the world, but Paul was bored. After a few minutes, he went out to the sculpture garden and started, as usual, to prove in conjecture. Paul's mathematics was like his politics. He learned mathematics in the 1930s in Hungary and England, and England at that time was a kind of mathematical backwater. For the rest of his life, he concentrated on the fields that he had learned as a boy: elementary and analytic number theory at the level of Landau, graph theory, set theory, probability theory, and classical analysis. In these fields, he was an absolute master, a virtuoso. At the same time, it is extraordinary to think of the parts of mathematics he never learned, much of contemporary number theory, for example. In retrospect, probably the greatest number theorist of the 1930s was Hecke, but Erdos knew nothing about his work and cared less. Hardy and Littlewood dominated British number theory when Erdos lived in England, but I doubt they understood Hecke. There is an essay by Irving Siegel in the current issue of the Bulletin of the American Mathematical Society. He tells the story of the visit of another great Hungarian mathematician, John von Neumann, to Cambridge in the 1930s. After his lecture, Hardy remarked, "Obviously a very intelligent young man, but was that mathematics?" A few months ago, on his last visit to New Jersey, I was telling Erdos something about p-adic analysis. Erdos was not interested. "You know," he said about the p-adic numbers, "they don't really exist." Paul never learned algebraic number theory. He was offended, actually he was furious, when André Weil wrote that analytic number theory is good mathematics, but analysis, not number theory. Paul's tit-for-tat response was that André Weil did good mathematics, but it was algebra, not number theory. I think Paul was a bit shocked that a problem he did consider number theory, Fermat's last theorem, was solved using ideas and methods of Weil and other very sophisticated mathematicians. It is idle to speculate about how great a mathematician Erdos was, as if one could put together a list of the top 10 or top 100 mathematicians of our century. His interests were broad, his conjectures, problems, and results profound, and his humanity extraordinary. He was the Bob Hope of mathematics, a kind of vaudeville performer who told the same jokes and the same stories 1,000 times. When he was scheduled to give yet another talk, no matter how tired he was, as soon as he was introduced to the audience, the adrenaline or maybe amphetamine would release into his system, and he would bound onto the stage full of energy and do his routine for the 1,001st time. If he were here today, he would be sitting in the first row, half asleep, happy to be in the presence of so many colleagues, collaborators, and friends. Yikadal v'kadash shemei rabbah yehi zikrono li'olam. May his memory be with us forever. So that was my talk. All right, reconsideration. So my brief talk at the Erdos conference was not intended for publication. Someone asked me for a copy, and it subsequently spread via email. Many people who heard me in Budapest, or who later read my eulogy, told me that it helped them remember Paul as a human being, but others clearly disliked what I said. I confess, I still don't know what disturbed them so deeply. It has less to do with Erdos, I think, than with the status of Hungarian mathematics in the scientific world. Everyone understands that Erdos was an extraordinary human being and a great mathematician who made major contributions to many parts of mathematics. He was a central figure in the creation of new fields, such as probabilistic number theory and random graphs. This part of the story is trivial. It is also true, understood by almost everyone and non-controversial, that Erdos did not work in and never learned the central core of 20th century mathematics. It is amazing to me how great were Erdos' contributions to mathematics and how little he knew. He never learned, for example, the great discoveries in number theory that were made at the beginning of the 20th century. These include, for example, the great discoveries in Weil's work on Diophantine equations, Artin's class field theory, and Hecke's monumental contributions to modular forms in analytic number theory. Erdos apparently knew nothing about Lie groups, Riemannian manifolds, algebraic geometry, algebraic topology, global analysis, or the deep ocean of mathematics connected with quantum mechanics and relativity theory. These subjects, already intensely investigated in the 1930s, were at the heart of 20th century mathematics. How could a great mathematician not want to study these things? This is the first Erdos paradox. In the case of the Indian mathematician Ramanujan, whose knowledge was also deep but narrow, there was a discussion in the literature about the possible sources of his mathematics education. The explanation of Hardy and others is that the only serious book that was accessible to Ramanujan in India was Cars, a synopsis of elementary results in pure and applied mathematics, and that Ramanujan lacked a broad mathematical culture because he did not have access to books and journals in India. But Hungary was not India. There were libraries, books, and journals in Budapest and in other places where Erdos lived in the 1930s and 1940s. For the past half century, Hungarian mathematics has been a term of art to describe the kind of mathematics that Erdos did. It includes combinatorics, graph theory, combinatorial set theory, and elementary and combinatorial number theory. Not all Hungarians do this kind of mathematics, of course, and many non-Hungarians do Hungarian mathematics. It happens that combinatorial reasoning is central to theoretical computer science, and Hungarian mathematics commands vast respect in the computer science world. It is also true, however, that for many years, combinatorics did not have the highest reputation among mathematicians in the ruling subset of the research community, exactly because combinatorics was concerned largely with questions that they believed incorrectly were not central to 20th century mathematics. In a volume in honor of Erdős' 70th birthday, Ernst Strauss wrote, "In our century in which mathematics is so strongly dominated by theory constructors, Erdos has remained the prince of problem solvers and the absolute monarch of problem posers." I disagree. There is, as Galfond often said, only one mathematics. There is no separation of mathematics into theory and problems, but there is an interesting lurking issue. In his lifetime, did Erdos get the recognition he deserved? Even though Erdos received almost every honor that can be given to a mathematician, some of his friends believe that he was still insufficiently appreciated, and they are bitter on his behalf. He was awarded a Wolf Prize and a Cole Prize, but he did not get a Fields Medal or a permanent professorship at the Institute for Advanced Study. He traveled from one university to another across the USA and was never without an invitation to lecture somewhere, but his mathematics was not highly regarded by the power brokers of mathematics. To them, his methods were insufficiently abstruse and obscure. They did not require complicated machinery. Paul invented diabolically clever arguments from arithmetic, combinatorics, and probability to solve problems, but the technique was too simple, too elementary. It was suspicious. The work could not be deep. None of this seemed to matter to Erdos, who was content to prove and conjecture and publish more than 1,500 papers. Not because of politicking, but because of computer science, and because his mathematics was always beautiful. In the past decade, the reputation of Erdos and the respect paid to discrete mathematics have increased exponentially. The Annals of Mathematics will now publish papers in combinatorics, and the most active seminar at the Institute for Advanced Study is in discrete mathematics and theoretical computer science. Fields medals are awarded to mathematicians who solve Erdos-type problems. Science has changed. In 1988, Alexander Grothendieck was awarded the Crawford Prize of the Swedish Academy of Sciences. In the letter to the Swedish Academy in which he declined the prize, he wrote, I can translate it, but I'm not going to read the French. He said, he wrote, "I am convinced that," I'm just translating it to English, "I am persuaded, or I am convinced that the only sort of decisive proof of the fertility of an idea or of a new vision is time. The fertility is determined by its descendants, and not by honors. Time has proved the fertility and richness of Erdos' work. The second Erdos paradox is that his methods and results, considered marginal in the 20th century, have become central in 21st century mathematics. May his memory be with us forever. So that was my little article. And if anyone has questions about anything I wrote or anything about Erdos, to the extent that I'm able, I'm happy to answer. If not, thank you very much.